Topic.
Topic 1. Van Haley's theory of geometric thinking.
Reporters.
Good day, everyone.
My name is Franklin A. Columbet.
And Maria Carmela Botar, and we are discussing the Van Hale model of
Geometric thinking. Van Hale theory describes how young people learn geometry. It postulates 5 levels of geometric thinking, which are the labeled visualization, analysis, abstractions, formal deductions, and rigor. Each level uses its own language and symbols. Students or pupils pass through the levels step by step.
This hierarchical order helps them to achieve better understanding and results. This article presents an overview of the model. It is focused on possibilities on how to apply this theory on Zizek mathematical education. Pierre Van Hale and his wife Dina Van Hale Geldof were Dutch researchers and teachers. They had personal experience with difficulties which their students had in learning geometry. Therefore, they dealt with these problems in detail. The theory originated in their thesis at the University of Utrecht in 1957. Pierre Van Hale devoted his lifetime to their theory, while Dina died shortly after completing their thesis. The theory has 3 aspects: the existence of levels, the properties of levels, and the progress from one level to the next level.
Now let's go to the Van Hale levels. According to the theory, there are 5 levels, or thinking or numbers, standing in geometry. Number 1, level 0 visualization. Number 2, level 1 analysis. Level 3, level 2 abstraction. Number 4, level 3 deduction. Number 5, level 4 rigor.
Level 0, visualization, or basic visualization or recognition. At this level, pupils use visual perceptions and nonverbal thinking. They recognize geometric figures by their shape as a whole and compare the figures with their prototypes or everyday things and categorize them. They use simple language and they do not identify the properties of geometric figures.
Figure number 1, level 1 analysis. At this level, pupils or students start analyzing and naming properties of geometric figures. They are not see a relationship between properties. They think all properties are important. There is no difference between necessary and sufficient statistics. So, as you can see, they are categorizing the square or the not square. Figure number 2 children at level identify only on the properties of squares.
Level 2 abstraction, informal deduction or ordering or relational. At this level, pupils or students perceive relationships between properties and figures. They create meaningful definitions. They are able to give simple arguments to justify their reasoning. They can draw logical maps and diagrams. They use sketches and grid paper.
Pierre Van Hale wrote, "The experience as the teacher of geometrical views means that all too often students have not yet achieved this level of informal deduction. Consequently, they are not successful in their study of the kind of geometry that English created, which involve formal deduction." Level 3 deductions. Formal deductions. At this level, students can give deductions geometric proofs. They are able to differentiate between necessary and sufficient conditions. They identify which properties are applied by others. They understand the rule of definitions, theorems, axioms, and proofs. And last but not the least, level 4, rigor. At this level, students understand the way how mathematical systems are established. They are able to use all types of proofs. They comprehend Euclidean and non-Euclidean geometry. They are able to describe of adding, removing, and axioms on a given geometric system.
Topic 2. Transformation.
Reporters.
Psychology of shape.
Reporters.
Psychology of shapes. The science studying the influence of shape on people and known as the psychology of shapes. Each shape has its own meaning and influences our minds and reactions differently. There are many psychological tests that are used to define the personality or mental condition. For example, a favorite figure can tell about a person's character traits. A quickly choosing shapes can show what's on the mind. The psychology of shapes is help for creating user-friendly interfaces. Psychology of shapes, all visual objects can be analyzed in terms of shapes. Example, house may be perceived as a rectangle with a triangle on the top, and the sun is often presented as a circle with lines around it. People may not always notice what figures and shapes surround them, still they have a great impact on our consciousness and behavior.
When we say psychology of shape, in a plane geometry, the two-dimensional shapes are flat shapes and closed figures, such as circle, squares, rectangle, rhombus, and etc. In solid geometry, the three-dimensional shapes are cube, cuboid, sphere, and cylinder. We can observe all these shapes in our daily existence also. For example, books, cuboid shapes, glasses, cylindrical shapes, traffic cones, conical shapes, and so on. And also they have types and properties of geometric shapes: triangle, circle, square, rectangle, parallelogram, polygon. When we say abstract shapes are depiction of real things without being exact preparation. A great example of abstract shapes is a stick figure which represents a person. Abstract shapes are super simple version of common elements or forms. Abstract shapes but lack true definition. Abstract shapes are recognized in form but are essentially not real as they are simplified version of organic shapes. And also we have organic shapes that often curvilinear in appearance that are similar to those found in nature, such as plants, animals, and rocks. The shape of leaves as well as those of another plant's parts are considered organic shapes. Organic shapes are figures that have a natural look and a flowing, curving appearance. Also, the organic or free-form shapes are shapes that seems to follow no rules. Organic shapes are irregular and imperfect. Organic shapes are areas of enclosed space with a length and width. Though they do not require geometry or mathematics, they appear free-form and natural.
Topic 4. Geometric pattern.
Reporter.
Good day, everyone. I am AC Viana Caridad Bonus, Bachelor of Secondary Education, major in English. And I am here to talk about
Geometric patterns.
a geometric pattern. You can find a pattern with objects, shapes, and features. For example, heart, followed by heart, followed by square, followed by heart, followed by heart, followed by square, blank, followed by heart, and followed by square. From the ideas of pattern heart, followed by heart, and followed by square, you can see what is missing from figure out what is next. And from this case, the missing shape is heart. Let's give another example. Which comes next in this pattern? If your answer is letter D, your answer is correct because the pattern is apple, watermelon, cherry. So the next fruits in the pattern is strawberry. Geometric pattern. The geometric pattern is defined as the sequence of numbers that are based on the multiplication and division operation. It's similar to arithmetic pattern. If two or more numbers in the sequence are provided, we can easily find the unknown terms in the pattern using multiplication and division operation. So, ang geometric pattern pala ay tumutukoy sa pagkakasunod-sunod ng bilang ng numero gamit ang multiplication at division. Kapareho din nito ang arithmetic pattern. Kung dalawa o higit pang numero ang pagkakasunod-sunod, madaling mahanap ang term ng pattern gamit din ang multiplication and division. For example, 9 followed by 18 followed by 36 blank followed by 144 blank. It is a geometric pattern as each term in the sequence can be obtained by multiplying 2 with previous term. For example, 36 is the third term in the sequence, which is obtained by multiplying 2 with previous term 18. So 18 times 2 equals 36. Likewise, we can find the unknown terms in the geometric pattern. The first missing term, the previous, is 36. What we can do to get the first missing term is to multiply the 36 times 2. So 36 times 2 is 72. So the missing term is 72. And the second missing term, the previous, is 144. So 144 times 2, we can get 288. So the missing term is 288. From this, the complete geometric is 9, 18, 36, 72, 144, and 288. Take note, kailangan mo lang malaman kung ano bang number ang pwedeng ma-multiply o ma-divide para malaman mo kung ano yung missing term. Thank you for watching. I hope you learned something about my topic.
Topic 5. Geometric concept enriching Filipino culture and arts.
Reporter.
Topic 6. Coding scheme.
Reporter.
Good day, everyone. I'm Renelen G. Casaol, BS Ed 1D. This is our tribe name, MATHANGEL. This is my topic about coding scheme. Coding scheme as a coding scheme is amenable to the comparison described about between the model of arithmetic. One can translate this coding into ones and the definable standard model and so convert this characterization of A to a formula defining from the degree A code for A, set for of degree A and standard different types of coding scheme to represent data. ASCII, American Standard Code for Information Interchange. It has definition for 128 characters 0x00 to 0x78 which are represented by bytes. Example, characters 0229 A to Z, A to Z. Decimal 48 to 57, 65 to 19, 97 to 120. Hexadecimal 30 to 39, 41 to 5A, 61 to 7A. UTF for Unicode Transformation Format 32 bytes. is a coding scheme utilizing a 4 bytes to representation a character. It was used to represent all of Unicode S, 112.0.64 code points. ISCII Indian Script Code for Information Interchange. It is a coding scheme which can accommodate the characters used by various Indian script. It is an 8-byte scheme. The first 128 characters are the same as ASCII and only the next 128 bytes space is used to represent ISCII specific characters. Thank you for watching.
Topic 7. Integer in computers.
Reporters.
Good day, everyone. I'm Rose Ann P. Bininsol.
Adeline F. Bascom from BSE 1D.
The topic that we assigned to us is all about integers in computer. First, what is integers? Integers is a number with a no decimal or fractional part. It includes negative and positive numbers, including 0. Also, integers represent a positive whole number or its negative value. Here is the example of integers: 0, 1, 2, 3, 4, 5, and negative 1, negative 2, negative 3, negative 4, and negative 5. An integers, in the context of computer programming, is a data type used to represent real number that do not have fractional value. Computer used a fixed number of bits to represent an integers. The commonly used bits length for integers are 8 bits, 16 bit, 32 bits, or 64 bit, where 1 byte is equals to 8 bits.
Integers are stored in binary format. Integers types in language come in different sizes on our computer we have. First, we have char, 8 bits. Second, short, with 16 bits. Int, with 32 bits. And long, with 64 bits. First, the char. Char types in integer types because underneath C stores integer numbers instead of characters. In C, char values are stored in 1 byte in memory and value range from 128 to 127 or 0 to 255. The short. Short is the qualifier and has 2 bytes and the value range is negative 32,768 to 32,767. And next, the int, short for integer. Integer is a fundamental variable type built into the compiler and used to define numeric variables holding whole numbers. Int has storage of 2 to 4 bytes with a range value of negative 32,768 to 32,767 or negative 2,147,483,648 to 2,147,483,647. I also have here long. The long data type store integers like int, but gives a wider range of values at the cost of taking more memory. Long store at least 32 bits, giving it range negative 2,147,483,648 to 2,147,483,647. And that's all. Thank you.
Topic 8. Binary, octal, decimal, and hexadecimal system. Reporter.
Good day, everyone. My name is Jessamine Alperin, BSED 1D. Binary number system. According to digital electronics and mathematics, a binary number is defined as a number that is expressed in the binary system or based on numeral system. It describes numeric values by 2 separate symbols, 1 and 0. The base 2 system is the positional notation with 2 as a radius. Octal number octal number system has a base of 8 and uses the numbers from 0 to 7. The octal numbers in the number system are usually represented by binary numbers when they are grouped in pairs of 2. The octal number system is base 8 and the octal symbol is 0, 1, 2, 3, 4, 5, 6, and 7. Decimal number system. In the decimal number system, the numbers are represented with base 10. The way of denoting the decimal numbers with base 10 is also termed as decimal notation. This number system is widely used in computer applications. It is also called base 10 number system, which consists of 10 digits such as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Each digit in the decimal system has a position and every digit is 10 times more significant than the previous digit. Hexadecimal number system. The hexadecimal number system is a type of number system that has a base value equal to 16. It is also pronounced sometimes as hex. Hexadecimal numbers are represented by only 16 symbols. These symbols or values are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F.
Topic 9. Operation on binary number.
Reporter.
Good day everyone, I am Catherine Benabayas, one of the reporter about the operation of binary number. Let's proceed to my discussion. What is binary number? Binary number is an operation that requires two inputs. Binary number represented by 0 and 1. In simple word, 0 is off and 1 is on, like switch of light. When we say byte is the basic unit of information in computer storage and processing. Also, it consists of 8 adjacent binary digits or bits. What is bits? It consists of a 0 or 1. Therefore, 0 and 1 is bits, while the byte is equivalent to 8 digits or bits. Always remember that binary numbers have 8 adjacent digits or 8 bits. These are 1, 2, 4, 8, 16, 32, 64, 128. What do you observe this arrangement? Yes, you're right. This always start at the left side to right, because if you start the number 1 at the right, the answer of computing the binary numbers will be wrong or not correct. And also, it multiplies by 2. Like 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on. Therefore, this is the arrangement of 8 digit or bits. Take note, always memorize the arrangement. Clear? Clear.
Observe the charts.
Let us compute the binary number by add, minus, times, and divide.
For example, addition of binary numbers into decimal. 1 0 0 1 1 0 1 1 0 1 0 1. Let's compute. Start from the left to right.
Magbe-base tayo ng pag-add doon sa pinakita ko kanina.
So, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0, carry 1, 1 plus 0 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry 1, bring down the 1, so this is the final answer. Let's put a column for the easier. Convert each binary number into decimal numbers. Again, memorize the 8 digits or bits. These are 1, 2, 4, 8, 16, 32, 64, and 128. Di ba nga ang 1 is on, so siya lang ang i-add. At ito na nga iyon. Therefore, 91 is the decimal number of 1,011,011. Let's proceed to subtraction of binary numbers. For example, 1110101 minus 1,000,000,100 is equal to, again, always start at the left side. 0 minus 0 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 0 is 1, and 1 minus 1 is 0. Let's put a column to get easier. Convert each binary numbers into decimal. Again, memorize the 8th digit or bits. This is the answer. Let's connect their bytes. So, 64 minus 32 is equal to 32, minus 8 is equal to 24, minus 1 is equal to 23. So, 23 is the decimal number of 0110101. Next, how to compute a multiplication of binary numbers. For example, 1001 times 101 is equal to, let's start at the left side. So, 0 times 1 is 1, 1 times 0 is 0, 1 times 0 is 1, and follow to the second up to third. See this, what I did. Look, I put a 0 on the column with the first in the left side because it's needed in computing a multiplication of binary numbers. Try to analyze and observe what I did. This is how to multiply a binary numbers. Therefore, let's add the numbers. This is the final answer. Again, yung may value lang ng 1 is yung i-add. 32 plus 8 is equal to 40, plus 4 is equal to 44, plus 1 is equal to 55. So, 55 is the decimal number of these binary numbers. Next division. 1010 divide by 10. So, 1 divided by 10 is 0. 1 minus 0 is 0. Bring down 0. 0 divided by 10 is 1. 1 times 0 is equal to 0. 1 times 1 is equal to 0. So, minus. Bring down 1. 1 divided by 10 is 0. 1 minus 0 is equal to 1. Bring down 0. So, 10 divided by 10 is 1. 1 times 0 is equal to 0, and 1 times 1 is equal to 1. Let's minus. 0 minus 0 is equal to 0. 1 minus 1 is equal to 0. Therefore, the final answer is 0101. Again, yung i-add ay yung may value lang ng 1. 4 plus 1 is equal to 5. 5 is the decimal number of 0101. I hope you understand and enjoy my lessons.
Topic 10. The basic logic gate.
Reporter.
Good day everyone, my name is Mary Albinosa and we are the tribes number 2. And our tribe's name is MATHANGELS. So today we're going to tackle about the basic logic gates. So what is basic logic gates? A logic gate is a digital gate that allows data to be transferred. Logic gates use logic to determine whether or not to pass a signal. Logic gates, on the other hand, govern the flow of information based on a set of rules. The following types of logic gates are commonly used. First is the AND gate, second is the OR gate, third is the NOT gate, fourth is the NOR gate, fifth is the NAND gate, sixth is the SOR gate, and the seventh is the NOR gates. So what is an AND gate? An AND gate has a single output and two or more inputs. The image in your screen is the example of an AND gate. Therefore, in AND gate, the output is high when all the inputs are high. The second is the OR gate. Two or more inputs and one output can be used in an OR gate. The OR gate's output will be given by the following mathematical procedure if there are two inputs A and B, y is equals to A plus B. The image in your screen is the example of OR gate. Therefore, in the OR gate, the output is high when any of the inputs is high. Third is the NAT gate. The NAT gate is a basic one input, one output gate. If there is only one input A, the output may be calculated using the Boolean equation y is equals to A. The image in your screen is the example of a NAT gate. The fourth is the NOR gate. A NOR gate, sometimes known as a NOT OR gate, consists of an OR gate followed by a NOT gate. The Boolean statement for the NOR gate is y is equals the quantity of A plus B if there are two inputs A and B. The example of the NOR gate is in the top of your screen, the image in the top of your screen. The fifth is the NAND gate. A NAND gate, sometimes known as a NOT AND gate, is essentially a NOT gate followed by an AND gate. If there are two inputs A and B, the Boolean expressions for the NAND gate is y is equals the quantity of AB. The image below your screen is the example of the NAND gate. The sixth is the SOR gate. The exclusive OR XOR gate is a digital logic gate that accepts more than two inputs but only outputs one value. The Boolean equation for the SOR gate is y is equals to A dot B plus AB if there are the two inputs A and B. The symbol for XOR gate is the image in your screen. The last gate is the NOR gate. The exclusive NOR or XNOR gate is a digital logic gate that accepts more than two inputs but only outputs one. If there are two inputs A and B, then the NOR gate's Boolean equation is y is equals to A dot B plus AB. The symbol of a NOR gate is the image in your screen. And that's all. Thank you for watching.
Topic 11. Text data.
Reporter.
Good day, everyone. My name is Vina Joy Esboreta, tribe number 2. Our tribe name is MATHANGELS, and today we are going to tackle about text data. Text data. Textual data comprise of speech and text databases, lexicons, text corpora, and other metadata added textual resources used for language and linguistic research. And what is text data used for? Text analytics is usually used to create graphs, tables, and other sorts of visual reports. Text mining combines notions of statistics, linguistics, and machine learning to create models that learn from training data and can predict results on new information based on their previous experience. And what is text data collection? Text data set collection is essentially a process of getting the data of text or text-like data from various origins. This helps you in developing technology that can understand human language in text form. For machines and applications to develop to this point, they need to consume humongous quantities of text data. And what is text data example? Your text data may be, as part of your research, example, survey responses, interview transcripts, collated as part of your research, example, journal articles for literature review, and writings of an author. That's all. Thank you.
Topic 12. Encoding and decoding.
Reporters.
Blessed day, everyone. Our lesson is all about encoding and decoding. Encoding and decoding are used in many forms of communications, including computing, data communications, programming, digital electronics, and human communications. So, in computers, encoding is the process of putting a sequence of characters, letters, numbers, punctuation, and certain symbols into a specialized format for efficient transmission or storage. Decoding is the opposite process, the conversion of an encoded format back into the original sequence of characters. Encoding and decoding processes for data communications have interesting origins. For example, Morse code emerged in 1838 when Samuel Morse created standardized sequence of two signal durations called dots and dashes for use with telegraph. Today's amateur radio operators still use Q signals, which evolved from codes the British Postmaster General created in the early 1900s to ease communication among British ships and coast stations. In programming, Internet access relies on encoding. A uniform resource locator or URL, the address of a web page can only be sent over the Internet using American Standard Code for Information Interchange or ASCII, which is the code used for text files in computing. Some ways of encoding and decoding are used in various programming languages include the following. In Java, encoding and decoding in Java is a method of representing data in a different format to efficiently transfer information through a network or the web. The encoder converts data into a web representation. Once received, the decoder converts the web representation data into its original form. In Python programming language, encoding represents a Unicode string as a string of bytes. This commonly occurs when you transfer an instance over a network or save it to a disk file. Decoding transforms a string of bytes into a Unicode string. This happens when you receive a string of bytes from a disk file or the network. In Swift, in the Apple Swift programming language, encoding and decoding models typically represent a serialization of object data from a JavaScript object notation string format. In digital electronics, the terms encoding and decoding reference analog to digital conversion and digital to analog conversion. The terms can apply to any form of data, including text, images, audio, video, multimedia, and softwares, and to signals and sensors, telemetry, and control systems. In human communication, people don't think about it as an encoding or decoding process, but human communication begins when a sender formulates or encodes a message. They choose the message they will convey in a communication channel. People do this every day with a little thought to the encoding process. That's all about encoding and decoding. Reported by myself, I am Bichayda Katlayadi from Section 1D. Let me insert Janice Baira. Thank you.
Topic 13. Error and error correction.
Reporter.
Good day everyone, I am Rayaan Bibinosa. Today we're gonna tackle about the error and error correction. What is error correction? Error correction is the process of detecting errors in transmitted messages and reconstructing the original error-free data. There are three major types of error correction. First, automatic repeat request. Second, forward error correction. And third, hybrid schemes. The automatic repeat request error management mechanism is provided by the LLC when an error is found in the receive frame at the receivers and to inform the sender to resend the frame. Forward error correction, or FEC, is a method of obtaining error control in data transmission in which the source or transmitter sends redundant data and the destination or receiver recognizes only the portion of the data that contains no apparent errors. Examples of error correction. The most classic example of error correction is the repetition code, where for each bit in an input message we duplicate each bit multiple times. For example, if you had message 0101, we could encode it using the repetition method and it would become 00111111 0001111. That's all. Thank you.
Topic 14. Repetition and Hamming code.
Reporter.